last piece of information we need is the linear density, so I need to measure the length and then the mass. So I have it pinned down at this end, and so then we're going to figure out how long this thing is. All right, so we need to go to the ends. We need to go to the ends of the thread there. This doesn't have to be the exact same piece that we used for doing the experiment. It just needs to be the same type of string, and I pulled it from the same spool. But we're basically going to the tip there. So it looks like just shy of 305 centimeters, or 3.05 meters, just shy of that. And now we need to find the mass. Notice that when I let go, it did extend back some, but remember when we ran the experiment, we had it stretched out, and so that's why I had it stretched out just then. So I've set up the triple beam balance here. I made sure that it was balanced, and to give a sense of how close that is. And now I'm going to put the string on it. This is the string I just met for which I just measured the length out in the hallway. And obviously it's big. Now, one of the reasons why I picked such a huge piece of string there is that I have found that finding the mass of this is a critical piece of the experiment. That the students who take the time and care get much better results than those who do not. Because the string has such a low mass, if you were off just a little bit here, that could have significant impact later on. That still seems a little bit off. So I'm going to pause till I get that set up. I think I just got that. All right, so there is that, and then I'll take a photo. This is the string vibrator right here. When you plug it in, it's not an on-off switch, it's just a plug and unplug. This thing is vibrating up and down, in theory, 60 times a second, because that's the way our current works in the US. And you can hear it against my fingernail right there. You can hear the purr of the engine also as it's going through the table as well. And we're going to hook that up to a pulley and some string and have just an absolutely rejoiceful lab. It is sagging the string, and so I've got to be careful about that. But it is about 0 degrees. I'm really not going to do much better. It looks visually parallel. At least the nice thing in the classroom is we have the brick mortar we could always use for comparison, but we just don't have that here. All right, so now I'm filming. There's the timer. All right, so I've got almost the second harmonic right here. It seems just a little bit off, and the reason why I can tell it's just a little bit off is over here. Over here, it's not quite at a perfect node. And so if we spend more time on the results here, the better we're going to get. This will be interesting to see what the camera actually picks up here, because what I'm seeing is very strange. All right, so we would have a node here, a node here, a node here, an anti-node here, and if you're not quite sure if it's an anti-node or not, you can just stick your finger right there. But the node, I should be able to stick it. Really don't hear it as much because it's not vibrating. Ideally, the node doesn't move at all. Whereas here, all right, so second harmonic, we have 2 antinodes, 3 nodes, 1,000 kilograms. All right, in order to get the first harmonic, we need to add tension. And this is the part, this is the most dangerous part, or the one that might cause the biggest trouble. So sort of push through. Almost see it. There's a node right there. Trouble is that this mass is getting really close to the table, and now the mass is on the table. Ooh, we're also moving that table. So I'm going to stop this and then come back once I have that set up. I have about 2,000 grams sitting on it right now. Notice that I've got, it looks like a node about here. So I'm going to need to add more mass in order to move the node that way. So we're not. All right, I want you to get a sense of the noise that's happening right here. Some students get to this point and they start backing off, but we need to keep pushing forward. The node is now here, and we need to get the node over to there. And that's the problem with this. All right, so after that accident, we had to basically re-rig it, and so I have a guy wire right here holding that in place. We're gonna have to redo the measurement. I had to move this table also. This table right here was getting pulled when I had the large amount of mass on it over there, so we're gonna have to redo that distance right there. Right now we have anti-node, node, anti-node, node, and then over here we have a node over here, but is this the best that we can do here? Do I need to lighten it up a little bit to get a better amplitude? And as I lift up on it, we get a bigger amplitude. So we actually need just a little bit under. Of course, we're losing the node over there. So we need just shy of this 1 kilogram mass. And so let's see if I can arrange that. That's about 900 grams right there. You can hear the sound sort of coming and going, as well as, again, we have an instability here, so we're not quite there yet, but I wouldn't have expected it to actually hit that second harmonic. So I have, based upon what's written on the masses there, I have 1,000 grams, which is equivalent to what we had before, and it actually looks very similar to what we had before. So I need a little bit less than that, so I'm going to take the 100 gram off and start putting on smaller ones. But at least with these, we can put them on the triple beam balance and actually get measurements of them. That is based upon what's written on there, 950. We have a much better amplitude there for the anti-node. It's basically running that big as opposed to before it was half that size, so we are much closer to it. And in terms of the node down here, that's looking decent there. Well, let's see if we can get a little bit better. We had one more issue over there as that fell apart, so let's measure this distance yet one more time. Basically, I'm having issues with holding the measuring tape and filming at the same time, and so I just went ahead and did it for you, and spoiler alert, it was 162.7 centimeters. That is without the filming, 162.7 centimeters, and we're going to just have to go with that. Down at that end, I have 970 grams based upon what is printed on there. We'll actually find a real number later. I'm really curious, again, what this thing is actually going to show. We're not quite there yet. This is a little bit unstable. We're not at something really nice yet. So let's just add a little bit of mass here. See if I add another 20, so we're at 990. Stabilize it, but it suppressed it a little bit there. So I took that off and it's destabilizing. So let's stick a 10 on there. That's not too bad. Let's see. I'm going to lift this up just slightly just to see. We can get better. So somewhere between something less than 10. Uh-oh. All right, I'm going to put this down. So we seem to actually have what we're looking for right there. So we have all that mass, and though we can actually now use the triple beam balance to figure out how much that is. So I'm running into yet one more issue in the fact that I'm doing this outside and the wind is causing issues. So I'm going to have to take some of this inside. I can't find the mass all at once, and also instead of dealing with the offset like I did in the previous lab, there's an adjustment over here that I messed with, and that's for slight adjustments there, and it actually seems just a little bit off. Let's see, still seems just a little bit off. And again, it might seem like, really, does that kind of tweaking really make that big of a difference? And philosophically, where it makes a difference is that if you are taking care of the little things, then the more important things actually come out much nicer. I guess it's the equivalent of the broken window theory of crime for science. That really is as good as I'm going to get. So I'm not putting all the mass on at once. I left the 500 gram mass out. This should be a little bit under 500 grams if what's printed on there is correct. Plus we also have one clip here. You know, as good as I'm going to get. So the back mass is on 70, the middle one's on 400, and that one is there. So those are units of grams. So that's in between 2 and 3 grams, and you can narrow it down better than that. So in between 2.8 and 2.9 grams. And so whatever mass you get from this set, you're going to have to add to the mass of what comes next, because this was, again, just the first part. This is the 500 gram mass, 500 just because that's what it says on there, but it's a little bit off. So we need to cut back a little bit. It's a little bit under 500 grams apparently, so let me pause it while I get that. So we have it there. It's looking even enough for me. And so the back one is on 90, the middle one's on 400, and this one is just shy of 499.9 grams. Just did was the second harmonic, so we wanted to get the first harmonic because it's going to be considerably more mass to it. So what I'm going to do is I'm going to add, I've got roughly 700 right there, so I'm going to add 1,000, and I'll just keep setting up, and I'm going to stop until I actually have it. So we have the first harmonic finally. Had some issues because the other 1,000 gram mass does not actually have a hook on it. It's been broken off, but that's where we are. I'm just shy over there. So I'm going to pause it and try to get that more perfect. That's looking like they're in the right place here. My hand's on this just to keep the pulley in the same position as it was before. And so now we need to find the mass of that big old mess there. This is the toughest one of all of them, at least the toughest in order to maintain. After this one, the rest should be easy as long as we can find them. All right, so this is for the first harmonic. We have to do this in several different pieces here. So we'll pause it till I have at least piece one done. All right, so this is one of the 500, in air quotes, 500 gram masses, and it's looking pretty close to spot on there. And so we have the back one on 90, the middle one on 400, and this one right there. This is the next one. This is the 500. This is the other 500 gram. And it's like this one actually might be a little bit over 500 grams. We have the second mass. This is again for the first harmonic. Second one balanced. The back one's on 0. The middle one's on 500. And this one is right there. This is the third installment for the first harmonic. I have it even up there. So the back one is on 60. The middle one's on 400. And the close one is there. This is the fourth installment for the first harmonic. Back one is on 90, middle one's on 100, and this one is there. Also have two 1,000 gram masses that we need to add to it, but the balance is not going to measure that, just because it only goes up to 610 grams. So, but we do have a smaller one here, and we have the duct tape. So I'm going to do that next. So this would be installment 5, 6, and then 7 is the last thing I'm going to measure for the first harmonic. All right, that is lined up. And so the back one is on 0, the middle one's on 200, and the one up front is right there. And that is installment, I believe installment 7 for the first harmonic. We've got, part of the deal with this is that when you're doing the measurements, you take it when you got it. So this is the 4th harmonic. We haven't done the 3rd harmonic yet. This is the 4th harmonic, and that is the mass that's hanging on the end there. So let's find the mass, the total mass for the 4th harmonic. We should be able to do this all in one setting. We don't have to break this up, which is fortunate. So we have the mass for, this is basically the 4th harmonic. So the back one's on 40, front one's on 200, and the front one is, try to eliminate parallax. Again, 4th harmonic. We have a 3rd harmonic here, and that's the mass sitting on it. So we now, and a 3rd harmonic because I have 3 antinodes, and so now we're gonna see how much mass that is. 3rd harmonic lined up. The back one is on 30, the front one, the middle one's on 400, and the front one is there.
Back at work. Her coworkers have experienced so much pain, despair, and death.
So we have 1, 2, 3, 4, 5. This is the 6th harmonic here. You might not be able to tell. Actually, it looked like there was an angle there where you actually could see. Again, we'll have to check this later as we do the editing. This is the 6th harmonic. So 1, 2, 3, 4, 5, 6. 6 antinodes and 7 nodes. And so that's the mass that's hanging on it. Obviously, we skipped the 5th harmonic, and we'll have to come back for that one or find the 7th one. Who knows what it'll be. All right. So this is the 6th harmonic. The back one's on 0, the middle one's on 100, and there is, there we go. That is the 5th harmonic right there, and I really, well, as I've said before, don't know what it's actually going to look like, but we have antinode, 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 antinode. We have the 5 antinodes and then node, node, 3, 4, 5, 6 nodes. That is the mass for it, and I think this is the last trial. Then it's cleanup time. All right, so this is the 5th harmonic, and so the mass that was hanging there. So the back one's on 40, the middle one's on 100, and
Story and what her actions.
so we have 2 speeds for a wave. So if I have a wave, a standing wave, in other words, I'm sending a pulse down and it's bouncing back and coming back and interfering with itself in constructive and destructive patterns. So I have speed is equal to frequency times wavelength because I'm basically oscillating a string back and forth. And that's also should be equal to the tension over the linear density of the string. If I'm looking at tension versus wavelength, with the relationship between the two, I know that the frequency squared is equal to lambda squared times tension over mu. If I am controlling tension and wavelength is the thing that's changing, if I plot lambda squared versus tension, then I want to solve, I want to get this into y equals slope x plus b form. And so in other words, I'm solving for lambda squared. So lambda squared is equal to the tension over the frequency squared mu, which is 1 over frequency squared mu times tension plus 0. So now I have it into y equals slope x plus b form. So the slope should be 1 over the frequency squared times mu. So if I'm using this to solve for frequency, I solve for frequency. Frequency becomes squared is 1 over mu times the slope, or frequency is equal to the square root of 1 over mu times slope. So if I could plot this for enough data points, then I should get a nice trend line, get the slope, and I can find the frequency. And that is indeed what happens in the string vibrator lab.